I just want to show you this as we get started here. I want to talk about vapor pressure in a second, but our oil, I let it sit that whole time I was recording, and our oil and water layer have not quite totally separated, but mostly. So you can see the oil on top. Kind of cool. If I threw another Alka-Seltzer tablet in there, oh, who am I kidding? When I throw another Alka-Seltzer tablet in there, it's going to start bubbling again. Watch. I'm gonna put a few pieces in. See? Homemade lava lamp. Super easy, cheap gift for people. Just put it in a bottle with a lid. Cool, right? This is possible because they do not have complementary intermolecular forces, right? You can get oil-soluble dyes, which could be kind of cool. I don't have any at home. I just have food coloring, which is water-soluble. Pretty cool. Okay. Anyway, so back to our conversation about how IMF applies to a few other vocabulary words besides solubility. Vapor pressure is one of those phrases that gets used quite a bit, actually, not always correctly. So remember that when you're measuring vapor pressure, it has to be in a closed system. Like, I can see the gas forming here. I know there's a vapor pressure, but I can't measure the vapor pressure of this right now because all of the gas is escaping into the environment. I need a closed system to measure vapor pressure. Look, my hands are still blue. And yes, I washed them. Not very soluble in water. My skin is better. Anyway, if we put a lid on this and put a pressure gauge on it, then we could measure the vapor pressure of the gas being evolved, and also the air that's trapped in there already, and the water vapor. It's all mixed together. If I then heated that flask, right, you're going to get what's called a Boltzmann distribution. That's this picture here. So the blue is lower temperatures. You can see that not very many particles, this blue shaded in area, not very many particles have enough kinetic energy to be gas. But if I heat it up, that's the red curve, much more, everything under the red curve here, much more of those particles have enough energy to be a gas. So that means it would have a higher vapor pressure. Okay. So we want to be able to think about if I have two different substances, which one will have a higher vapor pressure? In order to answer that question, you need to think about the intermolecular forces that are holding it together. Okay? So, for example, I'm going to move my picture out of the way. We have a series of chemicals here. There's actually four. There's a fourth one down here. Water is the blue one. So water has a boiling point of 100 degrees Celsius, 100 degrees, at atmospheric pressure, which is 760 torr. So this line represents 1 atmosphere of pressure. Okay, so normal room pressure probably. Okay, so we have to heat things up to 100 degrees Celsius at atmospheric pressure. If we have a lower pressure, say we're up on the top of a mountain, then you don't have to heat the water up as hot to get it to boil. That's why if you read the back of some baking recipes, like the boxes and such, it'll have different instructions for baking and cooking at high altitudes because there's a lower pressure. Okay? So anyways, if we compare the same pressure, 1 atmosphere, and these different substances. So I'm going to draw some structures here so you know what these molecules are. So diethyl ether means that we have an oxygen in the center. Okay, lost my cursor for a minute. There we go. With its 2 lone pairs like so, and then it has some carbons and hydrogens attached to it. And that's mirrored on the other side. So initially this looks pretty polar, but then you realize, oh, we're gonna repeat the same exact thing on the opposite end. So really it's not all that polar. A little bit of a dipole, but not a lot. Okay? Then we have ethyl alcohol, which is kind of similar. It has the same ethyl group, CH2CH3, but then we put an OH on the end of it. That's capable of hydrogen bonding, of course. So that's a stronger intermolecular force than this dipole is. And then we have water. We all know what water looks like, but I'm going to draw it for you anyway. This has two places where hydrogen bonding can happen because it has two hydrogens attached to oxygen. So water is really very polar. It has a hydrogen bonding capability. All these things together indicate as we go up in IMF strength, the boiling point increases. Okay. Here we have ethylene glycol. That has an even higher intermolecular force because it's shaped like this. You have that alcohol group on the end, then the carbons in the middle, then another alcohol group. It's like if you took ethanol and copied the other end of it. So ethylene glycol, fondly called EG, it's got a boiling point of like 380 something Celsius. It's very, very high. That's because it has two places where hydrogen bonding can occur. And it has more flexibility than water does in terms of the molecule shape. So anyway, that makes it a much, much higher intermolecular force. Okay, so we can use a graph like this to compare different pressures. You can also use a graph like this to compare what's happening at a particular temperature. So for example, if we look at room temperature right here, 20 degrees or so, we can see that the diethyl ether will have a significantly higher proportion of particles in the gas phase because it is closer to the boiling point of diethyl ether than it is to anything else. So that's what this kind of graph can help us with. It can tell us what's going to boil. First, if you just pick a pressure and go across, it could also tell you which one has more gas particles at a given temperature if you go the other direction. Another way to show that kind of information for a single substance, so we're only talking about one molecular compound, is to use a phase diagram. Okay? Each phase diagram is going to have a slightly different shape. Sometimes they label them for you, like this one is labeled already. Sometimes they don't. So we want to be able to identify some key points in this graph. The first thing is to connect our discussion about phase changes. I'm going to move my picture back out of the way. So I think I'll go with green. See how that looks. So here we have melting and freezing. That is not very easy to see. So we have melting and freezing that happens anywhere along this line. Okay? Anywhere along here. At these pressures and these temperatures, whenever you're there, you're going to be melting or freezing, depending which direction you're going, right? If you're putting energy in, it's going to go melting. If you're taking energy away, it's going to go freezing, like that. Vaporization is going to happen where you have the interface between the liquid and the gas phase. So I'm going to color that in purple. Right? And so that's all along this whole curve. Anywhere where the pressure and temperature fit into this area is where vaporization and condensation can occur. Finally, we have the last two, sublimation and deposition. That's going to happen anywhere along this red line right here. Again, lower pressures, lower temperatures. Some things are easier to get to sublimate than others are. Okay? But it's two factors, pressure and temperature both matter. The other points we want to be aware of are going to be the triple point. That's where all three, the exact pressure and temperature, it's only 1 point, one pressure, one temperature for each substance, where all three phases exist at one time. There are some excellent and very neat YouTube videos about this, so Google it. Look for triple point. I don't think that's going to give you anything weird. Anyway, you might want to throw in the word chemistry or something. I don't know. But there's lots of videos where people have been able to get the solid, liquid, and gas present at the exact same time. That's called the triple point. On the graph, it's easy to find. It's just where all the lines intersect. The critical point is also cool. The critical point, well, actually it's hot. Get it? I know that was funny. The critical point is essentially you heat something up so much that it's kind of this weird, it behaves as a gas, but not quite a gas. It also pours like a liquid. Also tends to be sometimes ionized at that point. The behavior of the fluid changes. So liquids and gases are both fluid. Okay, they both are fluids. Okay, meaning you can pour them, believe it or not. Beyond the critical point, you get something called the supercritical fluid, and they have completely different properties. So for example, about, probably 20 years ago, maybe 25 years ago, somebody discovered that if you take carbon dioxide and pressurize it and heat it up a bit, you'll get a supercritical fluid, which is really good at cleaning fabrics without damaging them. Many dry cleaners now use supercritical CO2 instead of a whole bunch of nonpolar solvents that make the environment polluted wherever a dry cleaner has ever been. Okay, so obviously CO2 is cheaper, it's less environmentally hazardous, you just harvest it from the air, use it, put it back. It's not a big deal. Okay, so I don't even know what this is the phase diagram of, it's just an example. I do want to show you though, when they have not labeled something and you just have 3 random lines and you don't know which one is solid, liquid, or gas, here's the trick. This is supposed to be a single line. Here's the trick. All you have to do is pick a pressure where you can draw a straight line through all of them just by increasing temperature. Okay? The lowest temperature is going to be the solid. So I'm looking at the x-axis here. The next is going to be your liquid. And the highest temperature one will be the gas. So as you increase temperature, it always goes solid, liquid, gas. I couldn't do that analysis with something down here because it's all gas, right? Okay. So that's a good way of doing it. Gases happen at low pressure, high temperature. Solids happen at high pressure, low temperature. And of course, the liquids will be in between. Once you have that sketch figured out, then you can identify where melting and freezing and all the other things are happening. Okay. So here's the phase diagram for just plain old water. The triple point of water is pretty low and very low pressure. This is the hard thing. Pressure that low is difficult to do. But if you could do it, then you would be able to see solid, liquid, and gas water all in one container, right? So that's your triple point. The supercritical point is actually really, really high, and this is because of the strong IMF between water molecules, right? It's going to take a lot of energy and a lot of pressure to get it to become supercritical. A lot of effort, okay? Of course, we exist, I'm trying to draw a straight line, let me focus, at about 20 degrees Celsius, which is, I don't know, somewhere in there, and 1 atmosphere. That's squarely in the liquid phase, right? Of course, in upstate New York, it gets a lot colder than that, so you know what happens then. Right? You're going to get a solid, no matter what the pressure is. Here's carbon dioxide. I just told you the story about it being discovered as a really cheap, much more environmentally friendly dry cleaning fluid. And that's pretty accessible because you just have to heat it up to 31 Celsius and pressurize it a little bit. Adding pressure is always easier than taking it away, by the way, but it takes energy to do that. So pressurize it a teeny bit, heat it up a teeny bit, and then you will have a supercritical fluid. So this is actually not a lot of energy needed to do that. If you've ever played with dry ice, that's CO2. That's compressed. So it's been squooshed down, high pressure, to make it into a cake, a little puck or a block. But at 1 atmosphere of pressure, we see at room temperature, which is probably somewhere here, we see it should be a gas. So your solid block of dry ice quickly starts to sublimate, right? It doesn't become a liquid at all because that's pressure is too low to be a liquid. Instead, it just goes straight from solid dry ice puck into the gas phase. You get all this vapor. It's pretty cool. All right. So that's it for this chapter. Hopefully you get to practice ranking things based on their intermolecular forces and identifying what kind of IMF they're going to have. Those skills are going to be super important when you go on into biology and organic chemistry and life. Okay? So if you know whether something is nonpolar, that means it only has London dispersion forces. You would use something oil-based to dissolve it. Similarly, if you know something is polar, you want to use something polar to dissolve